can AI models really reason? Or are they just, incredibly sophisticated pattern matching machines, just super fast?
It's a huge question, isn't it? It feels pretty fundamental.
Yeah, to understanding what AI is, what it might actually become. And now we've got these large reasoning models, LLMs they're calling them.
Right, the ones that show their work, that step-by-step thinking.
Exactly. And seeing that, well, it makes the debate even more intense. Are they thinking?
It really does. I mean, when you see a model output this long chain of thought and it looks logical.
It feels like reasoning, right?
It absolutely does. You start wondering, okay, is this something deeper? Are they really processing information differently?
But just as we're getting kind of excited about that, boom, a new study lands. And it's basically throwing cold water on the whole idea. They claim these LRMs hit like fundamental reasoning limits. They talk about an accuracy collapse on these complex planning puzzles.
And the title, right, The Illusion of Thinking. Doesn't get much more direct than that.
Not subtle. They really wanted to challenge that feeling, that perception of reasoning.
And they presented some pretty stark evidence suggesting these models just hit a wall.
Exactly. But you know how fast this field moves? Almost immediately, another paper drops.
Already? Wow.
Yeah, taking a really hard look at that first study and basically saying, hold on a minute. What if the problem isn't the model's reasoning, but maybe it's how you tested them?
Okay. So a counter-argument questioning the experiment itself.
You got it. And their title.
Right.
Perfectly named. The illusion of thinking.
Huh. I like that. It's like a scientific back and forth playing out right in front of us.
Right, at the absolute cutting edge of AI capabilities, and that's exactly what we're diving into today.
Sounds fascinating.
So this deep dive, it's custom tailored for you. We're taking these two papers, the direct sources, right from the researchers, and we're going to unpack this whole debate.
Looking at both sides.
Yep. What did the first paper really claim? What were the specific, detailed counter-arguments in the second one? And ultimately, what does this tell you about the challenge of actually figuring out if an AI is reasoning?
The goal is to give you the key insights, the surprising details from both papers.
Exactly. So you feel properly informed about this really critical discussion happening right now.
So we'll start with the illusion of thinking, the Shojay paper, which kind of set the stage with these observed limits.
And then we'll spend a good chunk of time on the response, right? The critiques and the counter evidence from the illusion of thinking, the Opus and Lawson paper.
Makes sense. Lay out the claim, then the critique.
Okay, so let's jump into that first paper. Shojay and colleagues, they wanted to get a handle on the actual capabilities and, maybe more importantly, the limitations of these newer LRMs.
Models like O3 Mini, DeepSeek R1, Claude 3.7 Sonnet Thinking, the ones designed for reasoning.
Right, and they felt that, the standard benchmarks like math problems or coding tasks, sometimes they have contamination issues.
Yeah, the worry is the models might have just seen similar problems during their massive training phase.
So you can't be totally sure if it's real reasoning or just like pattern recall.
Exactly.
Yeah.
It muddies the waters. So they looked for tasks where they could control things more precisely, the environment, the complexity.
And they landed on these classic planning puzzles, things like Tower of Hanoi.
Checker, jumping, river crossing, blocks world, stuff like that.
Yeah, and the neat thing is you can dial up the difficulty, right? Add more disks, more checkers.
Yeah.
But the underlying logic stays the same.
It gives you a controlled way to scale the challenge.
And here's the crucial part. They didn't just look at the final answer. Was it right or wrong? No.
They went deeper.
They dove into the intermediate steps, the thoughts the models generated along the way.
Trying to see the process, not just the result.
Exactly. How are they trying to solve it? Which is a very different question.
And their big finding, the headline from The Illusion of Thinking, was this accuracy collapse.
Right. What did that mean specifically?
They reported that across these different puzzles, once the complexity hit a certain point, more disks, harder configurations, the performance of these reasoning models just plummeted.
Plummeted? How badly?
Often down to zero accuracy. They just couldn't solve them anymore.
Wow. Zero.
Yeah, and they interpreted this as, well, evidence of fundamental limits, like the reasoning ability just doesn't scale up with the problem's difficulty.
They broke it down, didn't they, into different complexity levels?
They did. 3 regimes. At low complexity, surprisingly, sometimes the standard models, the ones without explicit thinking steps, actually did better.
Huh. Or more efficient, maybe.
Yeah, or more token efficient, exactly. Then at medium complexity, the thinking models, the LRMs, they did have an advantage. That made sense.
Okay.
But then at high complexity, this was the kicker, both types of models just collapsed, fell apart completely.
Both the standard ones and the reasoning ones.
Both, which strengthened their argument about a fundamental limit.
Okay, and what about the effort the models put in? You mentioned something counterintuitive there.
Right.
Yeah, this was really interesting. They measured effort by counting the tokens used in the thinking traces.
Okay, so more thinking, more tokens. Makes sense.
You'd think. You'd expect as the problem gets harder, the model would think more, right? Generate more steps, use more tokens trying to find the solution.
Right. Seems logical.
But Shoji et al. Reported the opposite. As the problems got more complex right near that collapse point, the model's thinking effort, the token count, actually decreased.
Even if they hadn't run out of tokens?
Even when they had plenty of token budget left, it looked like they were just giving up on thinking.
That is weird. Like they just check out.
Sort of. And the analysis of the thoughts themselves seemed to back this up. On easy problems, maybe they overthought, kept generating steps, even after finding the answer.
Okay.
Moderate complexity, they might explore wrong paths first, then find the right one. But high complexity, often no correct solution paths were found at all in the traces.
Nothing correct in the thinking process itself.
Pretty much. They also flagged issues with what they called exact computation. Like, for Tower of Hanoi, even when they gave the model the explicit algorithm, performance didn't improve that much.
Huh. Even with the instructions.
Yeah. And they saw weird inconsistencies. A model might handle thousands of moves correctly on Tower of Hanoi, but then fail super early on a river crossing puzzle that actually requires far fewer total moves.
So different types of reasoning trip them up differently, maybe.
That's what it suggested. So the picture painted by this first paper is pretty stark. Models hitting a hard ceiling, not scaling, struggling with precision, maybe even just stopping trying when things get tough.
Okay, so that's the setup. The illusion of thinking, strong claims.
Very strong. And this is exactly where Urbis and Lawson come in with the illusion of thinking. They zoom in on that Shoji paper.
Not just the results, though.
No. Critically, they look at how those results were generated. Their main point is maybe this collapse isn't about the model's actual reasoning ability. Maybe it's an artifact, something caused by the experiment itself.
The test setup.
Yeah.
The evaluation.
Exactly. Problems with the methodology, not necessarily the models.
Okay, let's really unpack their specific points from the source.
Yes.
This feels like where the real action is.
Absolutely. Their first big critique, it centers on output token limits.
Okay, the maximum number of tokens a model can generate.
Right. Opus and Lawson point out that the way Shoji et al. Set up the test for some puzzles, especially Tower of Hanoi, required the model to output every single step of the solution.
Not just the final answer or a plan, but the whole execution.
The entire sequence of moves. Now, for Tower of Hanoi, the number of moves needed grows exponentially with the number of disks, n. It's 2 to the power of n minus 1.
Okay, so it gets big fast.
Very fast. And if you have to output the entire sequence at each step, the total length of the output needed for the test, it grows quadratically. It becomes enormous.
Whoa, so asking it to type out the whole thing just balloons the required output.
Precisely. And Opus and Lawson say, look, the models tested have max token limits, right? Like 64,000, maybe 100,000 tokens. That's a hard stop.
Yeah, they can't go beyond that.
And they calculated for Tower of Hanoi, what's the maximum number of disks, n, where you could even possibly output the full solution within those limits. It turns out to be around n is 7 or n is 8 for most models.
And where did the first paper report the accuracy collapse?
Exactly, at or very near those sizes. N7, NE7, NA, NA9. Right where the token limit would physically prevent outputting the full solution required by the test.
That's a really strong correlation. It sounds less like a reasoning collapse and more like hitting a physical output limit.
It certainly points that way. And Opus and Lawson even cite examples from model outputs in replications.
What do the models say?
Things like, explicitly, the pattern continues, but to avoid making this too long, I'll stop here.
So the model knew the pattern, knew how to continue, but self-truncated because of length constraints.
That's exactly what it looks like. It's not failing to solve. It's choosing not to output the ridiculously long answer demanded by the test format. It's hitting a typing limit maybe, not a thinking limit.
Wow. Okay, that really reframes the collapse for Tower of Hanoi. What was your second critique?
It builds right on that. It targets the automated evaluation used by Shoji et al.
How they graded the answers.
Yeah. If your test demands these incredibly long outputs, thousands and thousands of tokens, and you grade it by checking every single character or token for perfect accuracy.
Uh-oh. I see where this is going.
Well,
even a tiny mistake means failure.
Exactly. Obis and Lawson give a really stark example in their paper. Let's say a model is incredibly accurate, like 0.99999 per token accuracy. That's getting it right 9,999 times out of 10,000.
That sounds almost perfect.
It does. But what's the chance of getting a perfect score across a 10,000 token sequence with that accuracy? Less than 37%.
Get out.
Yeah. And if the accuracy is just slightly lower, like 0.999, still really good, the chance of a perfect score on that long sequence drops below 0.005%, basically zero.
So a model could understand the puzzle, generate 99.9% of the steps correctly, but because of one tiny typo or misstep in a massive output, the automated grader marks it as a complete failure.
Correct. The grading system couldn't tell the difference between a model that was totally lost and one that was almost perfect but tripped up once, or maybe just stopped early because of the token limits we just talked about.
It conflates near-perfect performance on a long task with total inability.
It risks doing that, yes. It's a potential flaw in how capability was measured, tied directly to the demand for these extremely long, perfect outputs.
Okay, token limits, flawed grading. What was the third critique? You said this one was wild.
Yeah, this one is, well, it's pretty stunning. Opus and Lawson found that some of the puzzle instances used by Shoje et al., specifically for the river crossing puzzle, were mathematically impossible to solve.
Impossible, like literally no solution exists.
Correct. They point to existing mathematical proofs showing that certain setups of river crossing, like n equals 6 or more individuals with a boat capacity of 3, simply cannot be solved. There's no valid sequence of moves.
And Shoje et al. Included these impossible puzzles in their tests.
Apparently so. And they scored the models as failures for not solving them.
Wait, they penalized the models for not finding a solution to a problem that has no solution.
That's what Opus and Lawson claim.
That's like giving someone an unsolvable math problem and marking them wrong for saying it's unsolvable.
Exactly. Or their analogy. Giving a SAT solver a logic program, a formula that is fundamentally unsatisfiable, and then scoring it 0 when it correctly tells you unsatisfiable.
If anything, correctly identifying an impossible problem seems like good reasoning, right?
You could definitely argue that. It highlights a huge potential issue. If you're using purely automated evaluation, you absolutely have to ensure your benchmark questions are actually solvable and valid. Otherwise, you're not measuring what you think you're measuring.
Okay, these three critiques together. The token limits matching the collapse point, the super strict grading penalizing tiny errors on long outputs, and testing on impossible problems, they really do cast doubt on the original fundamental collapse interpretation, don't they?
They definitely provide a strong alternative explanation. The observed collapse, and even that weird decrease in thinking tokens near the threshold, starts to look like it could just be the models hitting these output limits and the evaluation system misinterpreting that behavior.
It wasn't just critiques, though. You mentioned Opus and Lawson had counter evidence.
Yes, and this is crucial. They didn't just poke holes, they ran their own tests. They took Tower of Hanoi with N15 disks.
N15, that's way into the collapse zone, reported by the first paper, right?
Right.
Where accuracy was 0.
Exactly. But here's the key difference. They didn't ask the models to output the full sequence of moves. That would be millions of moves, impossible with token limits.
So what did they ask for instead?
They asked for something much more concise, a generating function. Basically, a short piece of code, like a LUDA function, that could produce the sequence of moves if you ran it.
So asking for the algorithm or the logic to solve it, not the full verbose printout of the solution itself.
Precisely. A much more compact representation of the reasoning.
Then what happened when they asked for the generating function for N15?
Across multiple LLMs, they reported high accuracy. The model successfully wrote the correct recursive code to solve Tower of Hanoi N15.
Whoa.
And they did it using only a few thousand tokens, way, way below the typical limit.
So at N15, where the first paper said reasoning completely collapsed to 0, the models could demonstrate the core reasoning, the algorithmic understanding needed to solve it.
It certainly seems so.
The barrier wasn't their ability to figure out how to solve it. It was the specific demand to output millions of steps imposed by the first paper's test format.
That's the strong implication, yes. It suggests that for Tower of Hanoi, at least, the collapse was likely an artifact of the output requirements and token limits, not a true failure of the underlying reasoning capability for that puzzle.
That is a massive difference in interpretation.
It really is. And Opus and Lawson also had something to say about how complexity was measured, right?
Yeah, the first paper used solution length, basically.
Right, compositional depth. And Opus and Lawson argue that's maybe not always the best way to gauge how hard a problem actually is for an AI solver.
Why not? More steps seems harder.
Well, they contrast Tower of Hanoi with puzzles like River Crossing or Blocks World. Tower of Hanoi, yes, it has an exponential number of moves, 2 on 1, gets very long, but the actual decision at each step, if you know the recursive algorithm, it's computationally simple, like an O1 decision, constant time.
Okay, easy decision, just many, many times.
Exactly. Now, compare that to River Crossing or Blocks World. These might have much shorter solution paths overall, fewer steps. But finding those steps requires much more complex reasoning. It involves search, exploring different possibilities, checking constraints, maybe backtracking. River Crossing is known to be NP hard. Blocks World is PS base hard. These are formal complexity classes indicating really difficult search problems.
Meaning figuring out the next step is way harder computationally, even if the total number of steps is less than Tower of Hanoi.
Exactly. The computational difficulty, the search space complexity, scales much more brutally for those problems, even if the final path looks shorter.
Okay, that helps explain that weird finding from the first paper. Why models could do thousands of simple Tower of Hanoi moves but fail early on a shorter but maybe trickier river crossing problem.
Right. It's not just about the length of the solution, but the kind of reasoning, the search complexity involved in finding it. It suggests compositional depth alone isn't a perfect measure of difficulty.
Okay, so let's try and synthesize this for you, the listener. What does this whole back and forth tell us about AI reasoning? It's clearly not simple.
No, definitely not settled by just these two papers. But Opus and Lawson make a really compelling case, I think. What looked like fundamental built-in reasoning limits in that first study, well, they might largely be consequences of how the tests were run.
Limitations imposed by the experimental setup, the evaluation methods.
Right. The collapse could stem from hitting token limits, or from a grading system that misreads model behavior, or even from using impossible problems in the test set.
So the real tension here, maybe it's less about whether these LLMs can reason at all,
and more about whether our tests, our evaluation methods, are sophisticated enough, flexible enough to actually capture and measure that reasoning properly.
Especially when you factor in practical things like token budgets or demanding answers in super specific, maybe inefficient formats.
It really highlights just how tricky it is to isolate and evaluate something as fuzzy as reasoning in these incredibly complex, often opaque systems.
Yeah, the way we ask the question, the format we demand the answer in, the constraints we put on it.
All these seemingly small details can drastically change how we perceive the model's capabilities. It's a big lesson.
Absolutely. For anyone trying to understand AI progress, you've got to be critical about the benchmarks themselves. How was this tested? The results are only as solid as the test design.
Couldn't agree more.
So are LLMs hitting a fundamental reasoning wall? Or are we just testing them in ways that, well, maybe obscure their actual abilities? The first paper showed some worrying signs.
But the second paper offers a very strong counter-narrative, pointing squarely at potential issues in the experimental design itself. Artifacts, not fundamental limits.
And this deep dive into these sources, it gives you that shortcut right into the heart of a really current, really important scientific debate. It shows why careful experiments matter so much, and just how nuanced evaluating these powerful AI models really is.
It's a perfect example of science progressing through critique and counter-experiment.
Definitely. Okay, so here's a final thought for you to chew on. If, like Opus and Lawson showed for Tower of Hanoi, simply changing the required output format from that massive step-by-step list for just a short piece of code can suddenly make a collapsed reasoning ability reappear. What other apparent failures or limitations that we see in AI today might actually just be artifacts of our current tests or the specific ways we're choosing to interact with and evaluate these models? How much capability might we be missing just because we're not asking the right questions in the right way?
That's a really interesting question to ponder. How much are we limited by our own methods of evaluation?